What's the gradient at that point? Because there are no 2 points to compare by definition. So here's what they both did. They said, imagine a circle. Okay? We can picture a tangent along here. In fact, that's where our language of tangents first comes from. Okay? Now, it's hard to do the maths with this thing because you just got that 1 point. But if I can get towards this tangent and think of it in terms of something else that I can calculate, something which does have 2 points, then I can work with this. For example, if I put in a whole bunch of parallel lines here, okay? All of these guys, these 1, 2, 3, 4 that I've just drawn, what are they called? They intersect the circle twice. They're called secants. Right? These guys, right? These guys do have 2 points. So I'm just going to think of the circle because that's where your secant and tangent language comes from, and then we'll come over to a graph in a second. Can you see the length of the chord that's cut off by this secant, right? The length of this chord. As I get closer and closer to becoming a tangent, as I move this way, right? The length of that chord is getting smaller. You agree? Right? In fact, eventually, once you get to the tangent, the length of that chord is 0, is it not? It's not actually a chord, it's just a single point. That's why it's actually 0, right? So what Newton wanted to do was take this problem apart by thinking of it as one of these problems. He thought, what if I can understand the behavior of this secant. What if I could imagine it as it approaches a chord of length 0? If it approaches a chord of length 0. So both of these guys said, I need some language to talk about things that approach something which, I can't actually get to, but I can still do the calculations on it. So they said, let's talk about limits. They introduced this notation of something getting closer and closer and closer until you're actually there, right? You make conclusions off of things that you know so that you can draw some information about something you don't know. Okay, so now here's where the rubber hits the road. Draw for me a new set of axes. Let's just go first quadrant, that's all you need. Now draw for me a curve. And let's call this some function of x. Okay? Now, if what I'm after is the gradient of a tangent, okay? What I'm going to start thinking about is the gradient of a secant, and think about what happens to that as it gets closer and closer to becoming a tangent, right? So, in order to get a secant, that's not hard. You just pick any 2 points you like here and here, okay? And can you see, like if the actual point I'm after is like somewhere in the middle here, okay? If you were to draw that tangent, it's actually not that far off in terms of its gradient compared to this secant, right? Like I'm in the right ballpark, yeah? So I've got these 2 points. Let's get some values on this, all right? If I imagine this is some x coordinate, who cares what it is? I'll just call it x. I want it to be anywhere that I like. I want to be able to input some value there, okay? And what I'll do is, I'll think about going from that point and going a bit further, right? Going like a distance of, say, they call it h, okay? You can think that h is kind of like for height, but that's not the best description because it's further. Anyway, h is the convention. There are other conventions as well. Sometimes you'll see it called delta x. We'll talk about y in a second. Now, if that little distance there, it's just a small distance, is h, then what's the coordinate of this point over here? Or I should say the x coordinate. It's x plus h, right? It's just that plus that. That gets you over there, okay? So now, if I want to work out the gradient of this secant here, right? The gradient of the secant, I've got x coordinates. I'm going to need y coordinates, aren't I? Right? So let's come over to here and here, okay? Now, I don't know what this function is. It could be anything. It's f of x, right? So if this x coordinate is x, just x, right? What am I going to be up here? F of x. Good. So for example, if this were x squared, right? Y equals x squared, then that would be x, and this would be x squared, right? Simple. And this is x plus h, so my corresponding y value over here will be f of x plus h, whatever f happens to be. Okay, so now what have I got here? What have I got? What I'm working out is the gradient of the secant. right? The gradient of this guy here, okay? And it's literally just rise over run. It's just rise over run. Okay? So what's my rise? Okay, it's the distance between these 2 points, these 2 y values, is it not? Okay. What is that distance?
F of x plus h
Good.
minus.
This, take away this, yeah? That's all that vertical distance is, okay? So rise, I've got that. Okay, now run is the horizontal distance that I'm going that corresponds to that, which of course I've defined as just h. Right? It's just h. So if I have some value of x, wherever you like, okay, and I have some function, you define it to be whatever you like, okay, this will give me the gradient of a secant that's anywhere you want, okay? But I don't want a secant, really. What I really want is at a single point where this distance in here, I don't want it to be this big gaping gap in here, okay? I want it to close in. I want it to come together just like these guys are coming together, right? So what I want is this guy here, h, I want it to get very, very, very small. Does that make sense? Now I already have language for this, right? When it becomes 0, I'm going to get not a secant, but a tangent. Do you agree with that? Right? That's what I want. What I want is for h to be 0. Now h can't really be 0, because look, I have to divide by h. I can't really be 0. But I can think about what happens as I get closer to 0. I just have to say, tell me what the limit is. Right? Tell me what the limit is. Just like we looked at before, if I gave you a trivial example. Okay? We looked at evaluating limits like that. Okay? Now that function there that I put over here, it's got a hole at 5, doesn't it? You can't equal 5 because it's on the denominator, so x equals 5 is not going to work. Okay? But all I need to do is I just have to say, well, that top thing, what can you do to that top thing? I can factorize it. It's the difference of squares. Right? So it's going to be x plus 5, x minus 5. And because of that, our denominator goes, no problem. Okay? So at that point, I can say, oh, that approaches 5, and I can actually put in 5. So it, of course, it's just going to be 10. Right? So even though this original thing, I can't put 5 in, I can see what happens as it approaches 5. It's going to go there. Okay? From above and below, you can go ahead and try it out. Okay? So here, I can't put in 0, but I can think about what happens as I get ever closer to it. Okay? So this thing here, this guy is a big deal. Okay? This was Leibniz's and Newton's big watershed moment. They're like, I can't work out by just putting in 0, right? At least into this, which is what it is by definition, rise over run, but I can still do maths with it. I can still do maths with it, even if I can't actually put 0 in. This is what we call the first principles of calculus. The first principles of calculus. Right? What are we actually working out? We're working out the gradient of the tangent. Okay? But this started to get a bit awkward in terms of like talking about all this stuff. So they introduced new language and they introduced new notation. Okay? So the new language they introduced was they called this thing, right? Like I could get it at a particular point. I could get it at a particular point. But I could get it at any point I like, right? And it's going to change all the way. So rather than this thing, which has a gradient, okay? This thing over here is going to be a function. It changes, right? So it's actually called the gradient function. Because the gradient is going to take on different values depending on where you look, depending on what value of x you look at, okay? Now, in the same way, he said, look, this rise over run business, rise over run, it's not working because there's not really a run. It's not really a run, okay? So they said, look, this is just the change in y divided by the change in x. That's all that's really happening, right? So you guys know the symbol in science, right, for change is a delta. So they use a D for delta. And they say the change in y, that's rise, right? And you compare it, you get its ratio with its change in x. That's the run, except run is an inadequate word because there's not really any run happening here. right? So dy, change in y over dx, change in x, it means rise over run, but in that case where the rise and run are both tending towards 0, because you're looking at this infinitesimally small spot. The rise is going to be 0, the run's going to be 0, but you can still see how it behaves.